Welcome to Brain Vision.
Okay, so in this problem, we're told to use the results for the magnetic field at distance x from a loop of wire of radius r, which I've written here. So we want to use that result and apply it to an infinitely long solenoid, so with many, many, many loops of wire like this, to find what the magnetic field will be at any point along the inside of here. So they tell us that the solenoid has a density of turns, so N is the number of turns per meter. And so now we want to find the net magnetic field here. So all we need to do actually is just say the net magnetic field will be the integral of a single magnetic field from one turn of the solenoid, so this expression up here, and then just times the density of turns, and then integrate with respect to x along the whole length of the solenoid. So since we're saying it's infinitely long, that'll be from negative infinity to infinity. So if setting up this integral is a little bit confusing, it's very much analogous to doing like a mass integral. So if, for instance, we said that the mass density of just an object was lambda, so lambda is just the mass of an object per length, so mass per unit length. So you've probably seen before, we could say the total mass is just the integral of lambda dx. And then we'd usually integrate that from 0 to L across the full length of the object. So we're really doing like the exact same thing here. So we're getting our total number of solenoid turns just by integrating the solenoid turn density. So this is our linear solenoid density, just like this is our linear mass density. And we integrate across our whole object here, which is infinitely long. And then we just integrate along with the magnetic field to get the effect of the magnetic field for each one of those turns of the solenoid. So all we need to do then is substitute in this expression for B here to get our total B net. So we'll have mu naught I r squared over 2 r squared plus x squared to the 3/2. And so these r squareds might look a little bit weird here too. Or I'm sorry, the x squareds might seem a little bit off here. So we wouldn't expect the final term to have these kind of expressions in them, since it doesn't really make sense to say we're a distance x from a single loop. So really we're like a distance x from kind of this point we're arbitrarily calling the center of the solenoid. So probably these things are going to cancel out in the end. So we shouldn't really have any dependence on like what this position is. We'd expect the field will be uniform in this infinitely long solenoid. So probably this x is going to go away. But anyway, so next we have our magnetic field, and then we just have n dx here. So we have a lot of constants we can pull out. So we have mu naught I r squared n over 2, and we're left with the integral dx over r squared plus x squared to the 3/2. And that's from negative infinity to infinity. So as usual, do this integral in whatever way you'd like. You can do it with a u substitution. You can look it up in a table. And we should get that we still have this big constant. And then this is going to come out to be x over r squared times r squared plus x squared to the 1/2. And then we're evaluating that from infinity and negative infinity. So we can pull out the r squared in the denominator here, and then we'd be left with just x over r squared plus x squared to the 1/2. And that's pretty easy then to evaluate at infinity and negative infinity. So this r squared just won't really matter. We'll have x over x squared to the 1/2. So we're just going to have, when we put in infinity here, we'll basically just have 1 over 1 and then minus -1. So if we leave the r squared in there, this is actually just going to be mu naught I r squared n over 2. And then we would have 1 over r squared, and then minus -1 over r squared. So we can see all of these r squareds are going to cancel out, and then this will just be a 2 in here, so 1 minus -1. So it looks like it's actually going to simplify a lot, and we're going to end up with just mu naught I n. So as you'd expect, the more current flowing through it, the stronger magnetic field we have. And then just exactly linearly with the number of turns we have, or the density of turns rather, the magnetic field increases.